Hello and welcome. I hope you're having a fantastic day. I'm Maciej Rymar. I'm one of the authors in the paper I will be presenting today, and we'll be talking about tractability in temporal betweenness centrality. So just to give some background on the concept, we are in network theory, and we would like to measure the importance of a node of a vertex in that graph representing the network. So as an example, we can think of a flight network. And in particular, we want to measure how important one particular airport is in that flight network, right? So how hub-like is it? How important is it to the global connectivity in the flight network? And just to give some background on the concept, the earliest mention I was able to find about it was by J.M. Anthonys in 1971. I wasn't able to find their image, but nonetheless, I'd like to credit them because it's the earliest mention. Nonetheless, generally, the first formal treatment that is attributed to in literature is by Lyndon Freeman, who was a professor of sociology at UC Irvine, and he introduced it as a measure for quantifying the measure of importance that a node has in a network. Another important person with regards to this concept is Ulrich Brandes, who published a seminal paper in 2001, and many results are based upon his paper. His main achievements were reducing the space requirement to linear, as well as improving the running time from O of n cubed to O of n, where n is number of vertices and m number of edges. So for sparse graph, this is a big improvement, and we can imagine that many examples of networks are pretty sparse. So both of those factors are very big improvements on what had been known beforehand. And now to define betweenness centrality formally, let us have a look at this quotient. So this is the number of shortest paths going through between S and Z, going through V, divided by the number of shortest paths between S and Z overall. So if we imagine that information or some agents, something travels between two vertices in our graph and it elects to choose the shortest path, then we can think of this quotient as the probability that our particular path that is chosen will go through the node V. And of course, the higher this quotient is, the more important V is to the connectivity of S and Z. And then to get the full betweenness centrality of that particular vertex, we basically sum over all possible start points and destinations. So intuitively, just the higher this measure is, the more important this vertex is to the connectivity in a graph, right? So it also measures this happiness. And just to drive it home with an example, here we have a graph. So the colors are only there to separate parts of the graph. They don't have any particular meaning, but what does have a meaning is the size. They are scaled according to its betweenness centrality, all the vertices. And we can see that those two yellow vertices, have the highest betweenness centrality because they separate the blue ones from the green ones. All paths between those two, all communications between those two parts of the graph go through the yellow vertices. And as such, they have the highest betweenness centrality. Now, there is one more aspect of the concept that we haven't touched upon yet. So let us think back to this flight network again and happiness here. So imagine we're going from Berlin to London, to New York via London. And consider those two paths. So we assume that there are 4 flights basically, and they are all on the same day. So first route would be going from Berlin to London at 10 a.m. and then from London to New York at 2 p.m. And then the other route, quote unquote, would be doing that in the opposite way. So of course, only the first route is a valid route because we go forwards in time, and for the second, we would have to go backwards in time. So if we just use the simple static model, basically this static graph model of the flight network, then we would be losing some information. And with temporal graphs, we would like to retain this kind of information, and this is the type of thing that this model gets used for. And to define it formally, it's nothing too fancy. We have a static graph, and to a static graph, we basically add time labels which state, okay, this edge appears at times 2 and 4, this edge appears at time 6, and now other than those times listed here, the edge doesn't appear. So it's a fairly straightforward generalization. And then, of course, we also have to define what a path is. And also intuitively, we have a walk. A walk is a walk is a sequence of edges so that we don't go backwards in time. And then we can also differentiate between non-strict paths or walks and strict paths or walks. And the former deal with mean that we don't go backwards in time, and the latter mean that we also have to go forwards all the time. And as we'll see later, they provide for interesting differences, this non-strict versus strict difference. And then a path is, of course, a walk which visits each vertex only once. And just to give a few examples, the first one isn't a path or a walk because it goes backwards in time here. This is a temporal path, but not only a non-strict one because we stay at time 2. And this is a fully valid temporal path because we go forwards in time at all times. And then we'd like to talk about optimality in a graph. And for that reason, let us think back to this flight network again. So we have a few ideas. For example, let's say that I care about comfort. I want a direct flight, or at least as few changes as possible. And this leads us to shortest walks, right? So this is an optimal walk because it makes as few changes as possible, as we take as few flights as possible. Then, okay, maybe there's another scenario. Maybe there's an emergency and I need to get to my destination now. So I can spare some comfort. I can take a bit longer, but as long as I get there as soon as possible, I'm happy. Or maybe there's another kind of approach. Maybe I hate flying and I want my journey to be as quick and painless as possible. And that leads us to fastest walks. So we may have to wait a bit before we find this kind of optimal connection, but at least we'll be traveling for as little as possible. So that's the improvement. And finally, that's maybe not as much of a optimality criterion, but let's say that I hate waiting around in airports and I want to spend my travel time in the air. So let's say I'm new to flying and I love the feeling of being in a plane. And as I said, maybe this is a bit contrived in the scenario of flight networks, but if we imagine, for example, disease spread and our temporal network modeling people meeting at different times, then, for example, this particular disease can spread only if the time between meetings is not too large, right? Because otherwise the person might recover. And in this case, restless walks are a natural concept to consider, natural constraint maybe to consider. And just to show them again, right? So in order from top to bottom, we have a shortest path because it has 2 edges. Then we have a foremost path because it arrives at time 5, whereas the other 2 arrive at time 6. Then we have a fastest path because it takes only 2 units of time, whereas the other ones take 4 and 5 respectively. And now only the bottom path, is too restless because we never stay for more than 2 units of time at any times, at any node, except for the starting one, which we don't treat as part of the path in that sense. So recall this definition of betweenness centrality in the static graph again. So we defined it as a ratio based on this ratio of shortest paths to shortest paths that go through a vertex. And in the temporal case, as we have just seen, there are multiple natural optimality concepts. So we have seen shortest, foremost, fastest. We have seen this restlessness constraint, and we can take combinations of those and many more. And one can definitely make an argument that this is a natural optimality criterion that we should be able to treat. So the case is not as straightforward. Determining what optimal means in the case of temporal graphs is not as clear. And hence, we basically go around this issue by defining one betweenness variant for each optimality concept. So for shortest, we have a separate concept of betweenness centrality for foremost, and so on and so forth. And previously, this concept has already been studied by many people in many different works. And some results that have been shown include, for example, those which I have listed here. So there are some polynomial-time results, and there are some hardness results. So usually those are sharp P hardness, which is basically an equivalent of NP for counting problems, because betweenness centrality deals with counting basically, so this complexity class often pops out there. And one thing to note about those results is that they were all proven in this kind of ad hoc one-by-one manner. So for every one of the hardness results, we basically, or reductions had to have been shown from a hard problem, or similarly for polynomial time, an algorithm had to have been presented, which is polynomial time. So in our work, our goal was to somehow generalize this notion of optimality and then find some way to determine whether this arbitrary notion of optimality in a temporal graph leads to a polynomial time computable measure of betweenness centrality. And another interesting point here is to point out the difference between strict and non-strict prefix foremost paths. So paths are prefix foremost if they're foremost and all their prefixes are also foremost. So for this to be a foremost path, we would have to have that it's foremost, but also this is a foremost path and this is a foremost path. And for such paths, we can see that strictness determines whether it is polynomial time solvable or computationally intractable. So here, sharp P hard. And this was also one of the reasons why those kinds of subtle differences led us to trying to find some general criteria which can determine whether some betweenness problem is polynomial time solvable or not. And the way we went about it, we have started by defining cost functions, which are functions which go from walks in a graph to real numbers plus infinity. And of course, then, since it's a cost function, we say naturally that to define optimality, we say that, okay, we start with a starting point and destination and then call a walk between those two optimal if it minimizes the value of the cost function over all possible walks, assuming that this minimum is not equal to infinity. If all walks between two vertices have cost infinity, then we consider there to not be any optimal as C walks. And this definition naturally captures basically all optimality concepts, because in the worst case, we can say that, okay, we can basically do an indicator function. We say, okay, this walk is optimal, this walk is not. But of course, usually you can do something better than that. So for shortest paths, we can define the value of the cost function to be the length of the corresponding walk. And just like in static case, shortest walks are also paths. So this definition captures this optimality criterion. For foremost walks, we can say that, that the value of the cost function is the arrival time of the walk, so the last timestamp on the walk. But unlike shortest, foremost walks are not paths. So if we wanted to define foremost paths, then we would have to work a bit harder. Then we have also delta restless walks, which again, this delta means that we cannot stay in a vertex for longer than delta units of time. And here we have to do this kind of indicator function approach, basically. So we say that the cost is 1 if all differences between timestamps are less than delta, so if the walk is valid. And otherwise, we say that the value is infinity. And nonetheless, this is a valid cost function according to our definition. So this kind of thing can also be captured. But now this definition is very general, so we have to constrain it somehow to get back to polynomial time solvability, of course. And the way we do it is we define two properties that a cost function can have. We start by prefix optimality, which says that prefixes of optimal walks have to also themselves be optimal. And there is kind of a technicality here that I wouldn't like to spend too much time on, but I would like to mention it because it is relatively important. So if this is our walk and we take this prefix, then it has to be optimal according to the definition, but only among those walks which also arrive at time 5. So for example, if we are in the case of shortest paths here, and we have a path like that which has length 2 and arrives at time 5, but we also have this direct edge which arrives at time 6. This is completely fine according to this definition because the shorter path has different arrival time. So if this is the shortest path among those which arrive at time 5, this is completely okay. Then we have prefix exchangeability, which again deals with prefixes of optimal walks. And this time, if we have a prefix, so let's say we have this prefix of a walk again, and again we have the same thing, so it arrives at time 5, so it's a walk. And now the point is that we can replace any prefix with another optimal walk between the two vertices. So for example, if I have another optimal walk here to the same vertex, then what prefix exchangeability says is that, okay, I can replace this prefix of our optimal walk with another optimal walk and still get an optimal walk, right? So in other words, this blue walk also has to be optimal according to our definition. So assuming that this first part is optimal to our vertex, then the whole walk also has to be optimal. This is what prefix exchangeability means. And then we also define prefix compatibility, which is just the combination of the two. So prefix optimality says, okay, prefixes of optimal walks are optimal. Prefix exchangeability means that we can splice in an optimal walk in place of a prefix of an optimal walk to also get another optimal walk. And as a remark, all known optimality concepts which yield a tractable betweenness centrality measure can be described by such a prefix-compatible cost function. So at least as far as we are aware, all that have been studied can be shown to come from such a prefix-compatible cost function. So hopefully our definition is not overly strict in this case. And now, having described this prefix compatibility, we can finally state our main result in the paper, which says that, okay, if I have a finite prefix-compatible cost function, then the betweenness centrality of all those vertices can be computed in polynomial time. And how we do it is we combine Brande's approach with a Bellman-Ford algorithm and generalize them to the temporal case. But just to quickly also mention this finiteness criterion, so this is because in all generality, we're not talking about just sets of paths, but also of walks. So of course there can be infinitely many walks because I can, in many cases on a walk, do one cycle, do 2 cycles, do arbitrarily many cycles, and if all of those cycles, or infinitely many at least of those cycles, lead to optimal walks, then betweenness centrality is even hard to define, because if you recall, it's based on counts of optimal walks. So if I have infinitely many of them, it's not even clear what betweenness centrality is in that case. And so when we say here that this is finite, what we mean is that the cost function leads to finitely many optimal walks. And another note about this theorem is that this is mostly a classification result. So the polynomial bound is there in the paper. It is not extremely large, but it is also not very practical. So it wouldn't be very fast if we decided to run this algorithm out of the box. But on the other hand, one property that we have is that taking out one part of prefix compatibility does not lead to polynomial time computability. So we have shown that there exist cost functions which have just one of the two properties, and they still lead to sharp P hard problems. So hopefully this kind of justifies our definition of prefix compatibility. And finally, we can use this theorem to do some new classifications for betweenness centrality measures. And in our paper, we state that the following are polynomial time solvable. And of course, for sets of walks, we have to add this caveat. Then this is of course only true if the corresponding sets are finite. So like I've just mentioned a second ago, sometimes for walks there can be infinitely many foremost walks, for example. But if the walk sets are strict, for example, then the theorems will certainly hold. And another point worth mentioning is that, just like we've mentioned, all known, at least to us, optimality concepts which yield polynomial time solvable betweenness centrality measure come from such prefix-compatible cost functions. So in principle, we could have re-derived all the previously known polynomial time solvability results. So this theorem seems to be reasonably general. And now I would like to just summarize the whole work. So what we have done is we have set about to finding a unified approach to determining polynomial time computability of different betweenness centrality variants. The way we have done it is we have provided a general definition of walk or path optimality, and then defined crucial properties that these crucial constraints on this optimality criterion then that lead to tractable betweenness centrality measures. But of course, it's not over, and there's always room for future work. So for example, we could try and weaken prefix compatibility while still maintaining polynomial time solvability. So like we mentioned earlier, we cannot just directly take out one of the two components of prefix compatibility, but naturally maybe we can weaken one of them and still arrive at something which yields polynomial time solvability. Or maybe it would be possible to show that prefix compatibility is in fact necessary for polynomial time solvability, which would also be an extremely interesting result, of course. Another avenue of research would be improving the polynomial bound in the theorem. So like we said, currently the current bound is not very practical. So if we could make it so that you can run this algorithm out of the box and get something reasonably efficient in practice, that would be a major improvement as well. But other than that, that is it for the talk. Thank you very much for listening. I'll hope you have a great rest of the conference. I hope I convinced some of you to read the whole paper. Thank you very much. Have a good day and goodbye.